Look, I'm gonna be straight with you. When I first learned about Europa, I thought it was the most boring moon in the solar system. Just another ice ball floating in Jupiter's shadow, right? White, cracked, dead-looking. The kind of place you'd scroll past in your astronomy feed without a second thought. But here's the thing that keeps me up at night. Europa has been lying to us this entire time. Because underneath that frozen shell, underneath kilometers of solid ice that would take us decades to drill through, there's an ocean. Not a little puddle, not some frozen slush. A full-blown global ocean wrapped entirely around the moon. We're talking about more liquid water than exists in every ocean on Earth. Combined. Let that sink in for a second. This frozen rock that looks completely dead from space is hiding an ocean bigger than our entire planet's water supply. And it's been sitting there, right under our noses, in one of the coldest, most hostile environments imaginable. Now, here's where it gets interesting. Actually, scratch that. Here's where it gets absolutely terrifying. On Earth, wherever you find liquid water mixing with energy and chemistry, life shows up. It doesn't ask permission. It doesn't wait for perfect conditions. It just appears. In boiling hot springs, in Antarctic ice, in toxic waste sites, in the deepest, darkest ocean trenches where sunlight has never reached. Water plus energy equals life. That's basically the formula. So for the last few decades, Europa has been sitting at the top of humanity's most uncomfortable question. Not, could there be life somewhere out there, but how close might it already be? And honestly, that question terrifies me more than any sci-fi movie ever could.
So because of this giant ocean, we think that Europa is actually one of the best places in the solar system to look for life beyond the Earth.
But here's the brutal problem we've been facing. We can't touch the ocean. Europa's ice shell is absurdly thick. We're talking tens of kilometers in some places. Too thick to drill through with anything we currently have. Too thick to melt. Too thick to punch a probe into. The ocean might as well be on another planet entirely, even though it's right there. So scientists had to get creative. Because if we can't go down to the ocean, maybe, just maybe, the ocean sometimes comes up to us. For years, that sounded like wishful thinking. Because Europa's surface is being absolutely destroyed by Jupiter's radiation, anything fragile should be getting erased constantly. Any organic molecules that somehow reach the surface should be obliterated within days or weeks. If material from the ocean ever did bubble up through the ice, it shouldn't survive long enough for us to detect it. And yet, Europa's surface is covered in cracks. Long, winding fractures that stretch for hundreds of kilometers. They overlap, they intersect. They cut through older ice in ways that suggest movement, stress, flexing. Europa isn't some dead block of ice. It's being squeezed like a stress ball by Jupiter's gravity, over and over again, every single orbit. That squeezing generates heat. Heat that keeps the ocean liquid. Heat that might be cracking the ice from below. And for years, scientists have been staring at those cracks and wondering, are these just surface features? Or are they doors? Doors that occasionally open just long enough for something from the ocean to escape. Before we go further, if you're enjoying this deep dive into Europa, and trust me, it gets even wilder, hit that subscribe button. We're covering the cutting edge of space exploration here, and you won't want to miss what's coming next. Seriously, the next chapter is going to blow your mind. Now back to those cracks. The stakes here couldn't be higher, because if material from Europa's ocean can reach the surface, even briefly, it means we don't need billion-dollar drilling missions. We don't need to land. We don't need to crack open the ice ourselves. Europa would be doing all the work for us. All we'd have to do is recognize the signal when we see it. But, and this is a massive but, recognizing that signal isn't easy. Europa is far. Like, really far. Jupiter's radiation creates so much noise that it distorts our measurements. Our instruments see static mixed with real chemistry. And most of the data we have comes from missions that flew past Europa decades ago.
Minus 5, 4, 3, 2, 1. Booster ignition and liftoff of Discovery, hoisting harmony to the heavens and opening new gateways for
missions that weren't even designed to look for life. They were just trying to understand what Jupiter's moons looked like. So for a long time, Europa remained this tantalizing promise, a place of potential, not proof. We knew the ocean was there, but we had no idea what was actually in it. Until something changed. Not because a new spacecraft showed up with better instruments. Not because NASA held some dramatic press conference. But because scientists went back and looked at the old data with fresh eyes. They took measurements that had been sitting in archives since the 1990s. Data that everyone thought they'd already squeezed every drop of information out of, and asked a new question. Not, what does Europa look like? But, what might Europa be hiding? And buried inside that decades-old data was a chemical fingerprint that changed everything. Ammonia. Now, I know what you're thinking. Ammonia? That's it? That's the big discovery? But in planetary science, finding ammonia on Europa is like finding a smoking gun at a crime scene. Because ammonia is absolutely packed with nitrogen. And nitrogen is essential for life as we know it. Proteins need it. Amino acids need it. DNA itself can't exist without nitrogen. And here's the kicker. Ammonia doesn't just randomly appear on icy surfaces and stick around. On Europa's surface, ammonia shouldn't last. Jupiter's radiation should tear it apart molecule by molecule. Sunlight should break it down. Over geological time, it should completely vanish. So if ammonia is present now, visible in our current measurements, it means one of two things. Either it arrived very, very recently, or something is constantly resupplying it. And that's where Europa stops being a frozen moon and starts becoming something alive. I don't mean biologically alive, not yet, but active, dynamic, a system in motion. Because ammonia isn't just a signature of potential life. It's also useful for keeping oceans liquid in extreme cold. It lowers the freezing point of water. Its presence makes Europa's subsurface ocean more stable, more persistent, and way more chemically interesting than we ever assumed. Which raises a deeply uncomfortable possibility. Europa's ocean might not be isolated. It might not be sealed away behind an impenetrable wall of ice. It might be actively communicating with the surface. Right. Now, if that's true, then Europa isn't just a place that could theoretically host life someday. It's a place that may already have all the ingredients in motion. Water, energy, chemistry, and now nitrogen, circulating through its entire system. But here's the twist that genuinely makes me question everything. This discovery didn't come from new measurements. It didn't come from some next-generation space telescope or a modern probe with cutting-edge instruments. It came from reanalyzing data collected 30 years ago by a spacecraft that wasn't even looking for this. The clues have been sitting there all along. We just didn't know how to read them yet. And if you think about that for more than 5 seconds, it's absolutely unsettling. If ammonia was hiding in plain sight for 3 decades, what else have we missed? What other worlds are quietly signaling their potential right now, just waiting for us to ask the right question? Europa has always been interesting. But now it's deeply, profoundly unsettling. This isn't about some distant future where we might one day explore its ocean. This is about the possibility that Europa has been actively reaching upward, delivering pieces of itself to the surface, basically daring us to notice. And those cracks, those fractures we once dismissed as old scars, might actually be highways, active pathways connecting a dark, mysterious ocean below to the radiation-scorched wasteland above. If ammonia is traveling through those cracks, then something is moving, something is active, something is happening beneath Europa's surface right this second, which brings me to an uncomfortable truth that I think about way too often. The evidence didn't arrive with fanfare. It didn't come wrapped in a shiny new mission announcement with press conferences and champagne. It emerged quietly, almost accidentally, from old data that was re-examined with new techniques and fresh perspectives. And that means the most important discovery about Europa in decades didn't require going back there. It required looking closer at what we already had. But once you see ammonia in those measurements, you can't unsee it. Because now the question isn't whether Europa has the ingredients for life. The question is how long those ingredients have been mixing together in that hidden ocean. And if material from the ocean is actively reaching the surface, what else might be coming with it? I'm going to let that question hang there for a moment while we take a brief pause. If you're finding this fascinating, and honestly, how could you not? Smash that like button and drop a comment telling me what you think might be in Europa's ocean. I read every single comment, and some of your theories are legitimately better than what I come up with. Alright, that question about what else might be emerging from Europa's ocean. It leads us backward in time. Back to the 1990s. Back to a spacecraft called Galileo. Back to measurements taken for completely different reasons, because the real story of ammonia on Europa doesn't start with the chemical itself. It starts with the mission that unknowingly found it, and then stored the evidence away for 30 years. Here's what keeps me up at night more than almost anything else in this story. The most important discovery about Europa in decades didn't come from a brand new billion-dollar mission with state-of-the-art instruments. It came from data that was already sitting in our archives. Old data. Neglected data. Data that everyone thought had already given up all its secrets. Long before Europa became this obsession for astrobiologists, back before ocean worlds was even a category we cared about, NASA sent a spacecraft called Galileo to Jupiter with a pretty straightforward mission: explore the giant planet and its moons. Take pictures. Collect measurements. Try not to get fried by radiation. When Galileo launched in 1989, nobody expected it to completely reshape our understanding of where life might exist. It was just supposed to survive. Galileo arrived at Jupiter in the mid-1990s and spent years doing risky flyby after risky flyby past Europa. And I mean risky. Jupiter's radiation belts are absolutely brutal. Every single orbit through that environment was slowly cooking Galileo's electronics. Time was limited. Every measurement had to count. Here's the thing, though. Galileo wasn't designed to search for life. That wasn't its job. Its instruments scanned Europa's surface for geology. They measured magnetic fields. They analyzed charged particles. They collected spectra, basically chemical fingerprints from reflected light. But in the 1990s, the technology to fully interpret that spectral data didn't exist. Computer storage was limited. Processing power was prehistoric compared to what we have now. So much of Galileo's data was compressed, archived, and left incomplete. Think about that. We had this treasure trove of information from Europa just sitting there, partially analyzed, and then filed away because we'd squeezed out everything we thought we could get from it. Still, even back then, something weird stood out. Europa's surface chemistry didn't behave the way scientists expected. Some regions reflected light differently than others. Certain areas looked contaminated, like something other than pure water ice was mixed into the surface. Scientists suspected maybe salts from the ocean. Maybe sulfur compounds from Jupiter's volcanic moon Io getting splattered across Europa. But nothing was definitive. Just hints. Frustrating, tantalizing hints. And hints aren't enough in science, right? You need proof. You need confirmation. You need multiple lines of evidence, all pointing the same direction. So Europa stayed on the interesting but unconfirmed list. Worth watching. Worth eventually going back to. But not urgent. Years passed. Galileo completed its mission and was deliberately crashed into Jupiter's atmosphere in 2003 to avoid any chance of contaminating Europa. The mission was over. The data went into long-term storage. Scientific attention shifted to Mars, to Saturn, to the explosion of exoplanet discoveries. Europa became yesterday's news. But here's what I find absolutely fascinating about scientific data. It doesn't age the way theories do. As analytical techniques improved over the following decades, as our processing algorithms got smarter, as machine learning and spectral analysis tools became more sophisticated, scientists started doing something brilliant. They started revisiting old missions with new eyes, taking archived data and running it through modern analysis pipelines. And when researchers decided to give Galileo's Europa measurements another look, measurements that had been sitting untouched for literally decades, something unexpected started emerging from the noise. A chemical signature that didn't fit any of the old explanations. Ammonia. And look, I need to be honest here. At first, that signal was subtle, almost dismissible. Europa's surface is insanely complex. Jupiter's radiation environment creates so much interference that it can distort readings in weird ways. No one wanted to make a big claim about detecting ammonia without being absolutely certain they weren't seeing some instrument artifact or misinterpreting the data. So they tested it. And tested it again. They compared different data sets. They cross-referenced with laboratory experiments. They ran simulations. They checked their math 17 different ways. And every single time, the same pattern kept appearing. Ammonia. But here's what made it impossible to dismiss. The ammonia wasn't everywhere. It wasn't randomly scattered across Europa's surface like you'd expect from some ancient contamination or measurement error. It was localized, concentrated in specific areas. and that's what changed everything. The ammonia signature appeared strongest along Europa's fractures, those long cracks that slice across the moon's icy shell, not in the smooth plains, not in the heavily irradiated highlands, but specifically along features that suggest geological activity. Movement. Flexing. Once scientists realized that pattern, they couldn't unknow it, because ammonia shouldn't survive on Europa's surface for long, not exposed to Jupiter's radiation bath. That radiation is relentless. It breaks molecular bonds. It tears compounds apart atom by atom. If ammonia were ancient, left over from when Europa first formed billions of years ago, it should be completely gone by now. So finding it now, in detectable quantities, demanded an explanation. Either Europa somehow has a way to protect ammonia on its surface, which seemed really unlikely given the radiation environment, or the ammonia is being actively replenished, continuously, or at least recently enough that it hasn't been destroyed yet. And once you start asking where's the ammonia coming from, there's really only one obvious answer. The ocean. If ammonia exists dissolved in Europa's subsurface ocean, and all our models strongly suggest it does, then it would naturally rise up with liquid water through cracks in the ice. When that water-ammonia mixture reaches the surface and the water freezes solid, the ammonia gets trapped in the ice. And for a brief window of time before radiation tears it apart, it becomes detectable from space. In other words, Galileo might have caught Europa in the act of doing exactly what we've been hoping for, exchanging material between its hidden ocean and its surface, not through dramatic eruptions, not through explosive geysers shooting miles into space, but through slow, subtle, persistent upwelling of ocean chemistry, through cracks in the ice. This kind of process is technically called cryovolcanism, ice volcanism. But on Europa, it doesn't need to be dramatic to matter. Even gentle upwelling would be enough. Enough to carry chemical fingerprints upward from the ocean. Enough to leave clues behind, written in the ice, visible to our instruments. And ammonia. Ammonia is one hell of a clue. Galileo collected the data in the 1990s. 30 years later, we finally learned how to listen properly to what it was telling us. Which raises an honestly unsettling question that I think about constantly. How many other worlds are trying to communicate with us right now through old data, weak signals, and overlooked anomalies? Just waiting for someone to ask the right question or apply the right analytical technique? How much evidence of habitability, or even life itself, might be sitting in archives, waiting for the right person to notice the pattern? Europa might be the first place where we realize that life-building chemistry isn't carefully hidden away in an inaccessible location. It's actively leaking to the surface, advertising itself, leaving clues, and that leak is an invitation, not a guarantee, not a promise, but an invitation to look closer, to study harder, to take this possibility seriously. If we go back to Europa with modern instruments and find nothing, we learn something important about where life can and can't exist. If we find chemistry but no biology, we learn even more about the requirements and timescales for life to emerge. If we find something unexpected, something we weren't looking for, something that challenges our assumptions about what life can be or where it can exist, everything changes. Europa doesn't promise life exists. It promises relevance. It promises that whatever we discover there will matter profoundly for understanding our place in the universe. A world we once dismissed as just another frozen moon is now one of the most important locations in the entire search for life beyond Earth. Not because it's dramatic, not because it's shouting for attention, but because it's honest. The evidence is subtle. The signals are fragile. The conclusions are careful and measured. Scientists aren't making wild claims or overpromising what might be there. And that's exactly how real discoveries begin. Not with sensational headlines, but with quiet persistence and mounting evidence. Europa isn't shouting that it hosts life. It's whispering through cracks in its ice shell, in the language of chemistry, in signals we're only now learning to interpret properly. And for the first time in human history, we're starting to understand what it's saying. Before I wrap this up, I want to hear from you. Does this change how you think about where we should be focusing our efforts in space exploration? Should Europa be a higher priority than Mars? Are you as excited about Europa Clipper as I am? Let me know in the comments. And listen, if this video gave you a new appreciation for Europa and why it matters so much, do me a favor. Share it with someone who loves space. Someone who asks big questions about life in the universe. Someone who needs to know that we're living through one of the most exciting times in the history of planetary exploration. The next decade is going to bring us answers about Europa that we've been waiting centuries to get. Whether those answers lead to life or just to better questions, we're about to learn something profound. And I, for one, can't wait to see what Europa tells us next. Thanks for watching. I'll see you in the next one.